Hi, this is Dr. Hay. I'm going to show you how to find the electric field if you are given a function for potential. So for example, let's pretend that we are given this function v. It contains x, y, and z. These are position coordinates, and this is potential at these positions. So it's as if you think of a three-dimensional space, and at any x, y, and z, you know the potential at that value. All right, so we know how to get from we know how to get from E field to potential. We also know how to get from potential to E field if you're given the function. So also note that these variables, let's draw a circle around them. These variables have units. They must have units, otherwise this doesn't work out. So for example, the unit 3 must contain the units V per meter squared, so volts per meter squared, in order to have volts on the other side. So similarly, 8 and 4 also have to have units in order for that function to be a real function. Okay, let's find the E field here. All right, you can see that I have filled in the partial derivatives. So what it means to take a partial derivative is, all right, for example, this first one, 6x is the derivative of this function v with respect to x while treating all the other variables z and y as constants. So you think of z and y as just like 5 or 13, so just some numbers multiplied here. But x is the variable that we take the partial derivative with respect to. Now I've kept this I hat here that's sitting right there. Okay, and I've done the same thing with the other ones. I've taken the partial derivative of v with respect to y and set it in front of j hat. That's this one sitting right here. And I've taken the partial derivative with respect to z of the entire function, treating everything else as constant, and left with only negative 24 z squared times k hat, and I've pulled down the k hat and left it sitting there too. Now you can see that I've gone from a scalar, this function is a scalar, to a vector. And I've pointed that out up here as well. Notice that E is a vector. Gradient is not often written like this. You can write it either way, but I'm writing it like this right now for you to see that in order to get from a scalar to a vector, you have to multiply by this, or you have to take an operation that is a vector. All right. So one thing I could do with a question like this, for example, if the question also said, find E at a specific location, well, now I know E at, all locations at any given x, y, and z. So if the question said, find E when, x is 2 centimeters, y is 3 centimeters, etc., I could plug in those values for x. Y doesn't show up here, so apparently it's the same for all y. And z, if I'm given a z, and I could say E is specifically this vector given a location. So E is specifically this vector at a location. So I could find a little tiny arrow in all locations in 3 dimensions to represent the E field. But let's do something else here with this. Let's check out this equation here and show that we can go backwards from an integral to a derivative and vice versa. Okay, so now I'm going to find the potential given this E field and see if I get what we started out with. All right, what I've done here is written my E vector. I've distributed the negative sign in. I've put it into this integral here for change in V. Change in is not the same as gradient. Notice these two symbols are different. And I've also put in a tiny bit of length. That's what this ds stands for here. I've put a little bit of length in the x direction times the I hat, and y, j hat, and z, z hat. Or I'm sorry, k hat, which represents the z direction. Okay, so now I'm going to take the dot product. Remember that multiplying I hats together, so for example, if I take this and multiply it by this, I'm going to get something. If I take I hat and multiply it by j hat, I'm going to get nothing, because two perpendicular vectors do not give value. They give 0 when they're dotted together. This is a dot product. When you multiply vectors, you have to specify what kind of multiplication you're doing. It's not just a regular multiplication, so it's a dot product. Let me show you what you're going to get. Now I want you to notice something. What I get is not a vector anymore. It is a scalar. The result of a dot product is a scalar. So I have taken all of the I hat components and dotted them together, all of the j hats and dotted them together, and all of the k hats and dotted them together. And this is what I end up with, and now I need to take the integral. Okay, here's the result of those integrals. V is equal to this function, and V is equal to, turns out, the same thing that we started out with. So that's an example showing you that you can take the gradient of V to find the electric field and you get a vector, and you can go backwards and take the integral of E with this dot product there and find the potential.